Hello, Maritz here, and this is a short video on work and energy. And the first thing we will look at is the concept of work. So say we have work surface somewhere over, say there. And on that surface we have some block of wood or something, and we drag that along the surface, and one might guess that we need to have some kind of force. Try to draw that a bit nicer. Okay, that we need to have some kind of force acting on it, because first, of course, we need a force to accelerate it, but secondly, we might have some force of friction also here that counteract the motion. But it makes sense that the more force you need, the more work you will have to do. If this is heavier, say we have another mass on top of this, we can guess that it costs twice as much to move it a certain distance. So what we can guess from this is that the work should in some way involve the force. It should be proportional to the force. Secondly, if we move this a certain distance and then we move it the same distance again and say the same distance again, we can it makes sense that the amount of work you need to put into this is proportional to the distance you move it. If you have to move something twice as far, then the total energy required, or the total work required we will put into this will be twice as much. I use the word energy there, but we'll get back to that in a second. So in the end we will get this, and that will actually be our definition, that work equals to the force in the direction of the motion times how far you moved. So the force times the distance. An example of this is, say you have a block and you want to lift it. So you lift this up, and the force required to lift something, remember this, that force equals mass times acceleration, and in this case the acceleration you work against is g, so we will use mg. Remember this, that acceleration of the earth is 9.81 meters per second square. Actually, that is the number we use. It's slightly different on different places. So that will be our force. Say this to make stuff simple for us. Say this is 1 kilogram, and you want to lift this 1 meter. In this case, the work will be the force required, which is 1 kilogram times 9.81 times how far we lift it, which is 1 meter. So this will give us a 9.81. Okay, we have a problem with the units here. Actually, I will erase this and write it down here. Equals to 9.81. And if you look at the units here, we can see that we have a force that is in newtons, and we have a distance in meters. So the unit for this would be Newton meters. Okay, so we can write up here that the unit for work would be Newton meters, but we will actually not use that. Newton meters will be used for something else. What we will use instead is the joules of a joule. I write the joule with a small letter there, since it's not a person, it's the unit, but for the, and that looks almost like a Y, we change that to make it look more like a J, capital J for that. So if we go back here, we will say that that is 9.81 joules to lift 1 kilogram 1 meter. So approximately 10 joules, and that gives you somewhat a feeling of how big a joule is. If you have to lift 1 kilogram 1 decimeter up there, say this book is 1 kilogram, and I lift that a tenth of a meter, that would cost me about 1 joule. So that gives a feeling about how big a joule is. So that is work. When I lifted the book up, as I took this book and I lifted up, I will actually, the work I put into this will be stored as potential energy in the book. So we can say that the work we do can be stored, and when we store it, we call it energy. More on that in the next video. Thank you.